Okay, so let's welcome Dr. Gabriella Gilli from the Institute of Astrophysica in Andalusia, Granada, where she now is working. And brief introduction to you may not know her. She's an expert in the Venus atmosphere, also on Mars atmosphere, can say. She did her PhD or finished her PhD during the Venus Express mission, and she worked in the thermosphere region and atmosphere region on radiative processes, on photochemistry, also on the non-local thermodynamic equilibrium, and she was also involved in a lot of data analysis, and I think also tried to retrieve the code related to the measurement of CO, which I found in these atmospheric layers. Then she was a postdoc in France, where she was more or less in charge at the Laboratory of Meteorologic Dynamic, LMD, it's in Paris, I think, right? Yeah. On the adaptation of a global circulation model to the Venus atmosphere. And then you were also in Portugal, at the Instituto de Astrofísica de Ciências. Please forgive my Spanish. And there she also got a grant, a Marie Curie grant, in a relation to hot terrestrial exoplanet atmospheres, so which is also related with some kind of comparison to exominus planets maybe and climate models. And then you're also involved in Ariel, as I have seen, and then the Europlanet coordination issues, I think, with Spain, Portugal, at least. You may not even know. No. And yeah, today she will talk about, now you work again in Granada, and she will now give you an overview on the preparation of modeling of what is the updates of the Venus atmosphere and also for future Venus missions. So the floor is yours. Thank you.
Thank you very much for the introduction. Thank you for inviting me, first of all, for the organizer for a very nice opportunity to talk about Venus. In particular, we talk about Venus atmosphere, which is the topic of my research. Made a selection of current knowledge of Venus atmosphere and fusion mission. Here. So after, just to give you an overview of the talk, I will first give you a short introduction, a selection of open questions. We'll talk about the last decades to Venus and the future decades of observation to Venus, which is very exciting. I will talk a little bit about the model I work with, the Venus general circulation model, a Venus general circulation model. And I will end up with kind of application of the Venus general circulation model to use Venus as a natural laboratory for exoplanets. In particular, to study close in orbits, Earth-like planets that can be similar to Venus. Okay, how the atmosphere of terrestrial planets? I know that you are atmosphere people, so I'll talk a lot about that. Just Venus and Mars are mainly composed of CO2, and the Earth, we are in a privileged position because we have a mean temperature so far of 15 degrees Celsius, plus or minus 2. While Venus is high with a scorching temperature on the surface, about 450 Kelvin, Celsius. Sorry, I'm used to talk about Kelvin and Venus, but then I have to talk about the Celsius degree. And Mars is a relatively cold planet with an average temperature of 70 degrees below zero. Venus is the closest planet to the Earth, so it's easier to reach. And however, if we consider, actually, it was the first planet that was, it comes later because I have to say something before. It was the first planet that was reached by satellites, in particular with the ex-Soviet Union program Venera. and probably you are aware of that some of the, most of them were very successful, some of them not, like the Cosmos 482. Maybe you are aware that it was falling 50 years later on the Earth, and it ended up in the Indigo Ocean. So despite of that, being so close to the Earth and so easy to reach, Venus is not one of the more, the space exploration, it goes all to Mars. We had very few missions on Venus. Actually, right now, there are no space missions observing Venus, and there are like 16 satellites around Mars. 8 of them are currently observing the planets. So is Venus really the Earth's twin sister? Yes and no. Yes, because they both form in the same protoplanetary disk. They have similar mass and size. However, as you know, Venus is completely covered by sulfuric acid thick clouds. So it's a toxic planet, let's say, a toxic place to live. However, studying Venus, it would be like it's very useful to make the link between habitability and planetary evolution. And it's something that you at this institute you are working actually very actively. So the 1 million the early phase when it was like the Earth and the magma ocean phase, till now, present day, when Mars, Venus and the Earth are such different worlds. So there are basically two main, I will talk about two main scenarios. There's not clear how the path that Venus took during this time. And one of the main unknown is the fate of water, indeed. So one of the main, the first tentative scenario suggests that Venus was already dry since the beginning, like 100 million years after the magma ocean phase. The magma ocean was solidifying slowly, so we had higher temperature, and instead we had injection of water vapor from volcanic activity into the atmosphere. So the total, the amount of water that we have was quickly going to space by hydrodynamical escape. So this is one of the scenarios. So Venus was pretty similar than it is today, like very soon after the magma ocean phase. The second scenario, starting with the second scenario, Venus was kind of wetter and more temperature, with a more temperature climate than it has today. This scenario, the magma ocean was solidifying very fast, so we get the temperature, good temperature for condensate kind of ocean. So ocean could have been on the surface of the planet for an undefined period of time. We don't know how much. There are some theories which suggest that between 1 and 4 giga-years, some geological events would have injected CO2 into the atmosphere, started the runaway greenhouse effect, so warm up the temperature, and the CO2 was trapped, kind of, let's say, into the atmosphere. So this was kind of similar path than on the Earth, except that on the Earth we have plate tectonics, so the CO2 is recycled to form carbonates. So it's not, let's say, trapped into the atmosphere. So this is one of the $1 million questions that the future missions to Venus want to reply. We have from the NASA side, let's say, DAVINCI and VERITAS. DAVINCI probably will be launched in 2029, so with the first mission to be launched to Venus. Let's say that those missions came like 15 years after the last missions, kind of. I will talk also about Venus Express and Akatsuki. So we have like an empty space between the previous decades and the new decades. This space is 15 years, 20 years. So DAVINCI will basically observe the composition of the deep atmosphere. We'll have an empty probe to measure noble gases. VERITAS will be debated, we don't know yet, but probably no early than 2031. It will be mostly focused on the surface. We'll have a kind of map, better maps at Magellan, and in high resolution and larger, will observe a large part of the planet. And here we have EnVision. EnVision was adopted in 2023. It's an ESA mission. It's the second ESA mission. The first was Venus Express. This is in collaboration with NASA. The launch is foreseen. I will talk more about EnVision, the next slide. It's foreseen in November, delayed 2031, with the starting of operation phase in mid-2034. At IAA, we are collaborating with we are in Guai ship, both for them. So we are working on the technological part and the technological development and the scientific part. And then the last but not the least, we also have China and India that was new mission. We probably always say, I read this morning still that the launch is proposed in 2026, tomorrow. It means over 2 hours in science exploration. And India also proposed a mission, but it's to be, I don't know if it's accepted or not. And voices will be kind of very similar to VERITAS, actually focused on the surface. The last decades, we had Venus Express, in which people here in the room collaborated actively. I was also working on Venus Express, in particular with VIRTIS instruments. Venus Express observed from 2006 to 2014, mostly actually focused on the atmosphere of the planets. I listed here a few highlights, a selection of highlights that the Venus Express obtained. As we can see here on the right, this is a variable and a stable polar vortex. In the South Pole, it was observed by Pioneer Venus in the North Pole, and it was also observed in the South Pole. It's one of the most variable and dynamical structure in the solar system because it changes the shape, the center, in terms of 24 hours. So it's extremely variable. Then the indirect evidence of a major volcanic eruption, because we found, I think it was VIRTIS also, was detecting at the cloud tops 70 kilometers, an increase of SO2 abundances, and then it's followed by a sudden decrease. So it could be kind of indirect evidence of volcanic eruption, but we have to investigate more with EnVision regarding this high variability that we found of SO2. Venus Express found that Venus is slowing down at the spinning of Venus. Condition that was Lumila was asking for CO2 to freeze out as ice was no determinator. That had to be also checked with models. And the large amount of water lost into space over the last billion years. Then we should have almost at the same time Akatsuki. I don't know if everybody knows the story, that was launched in 2010, was supposed to ride to Venus. But earlier than 2015, but it was a propulsion problem. We kept the satellite to enter into Venus orbit, but Japanese were so great that 5 years later managed to put the satellite again in the orbit of Venus, and so we had this observation thanks to this the great work of Japanese people. It was mostly focusing on the atmosphere and on the dynamics of the atmosphere. But here on the right, an example. For example, the Akatsuki found this big stationary gravity wave. It's one of the largest also structure of the solar system. It's like 10,000 kilometers long. And it's kind of stable, which is surprising considering that Venus atmosphere rotates very fast, 60 times faster than the solid body. So we have like 100 meters per second which is the superrotation, and here we have kind of stationary gravity waves. So it was a kind of surprise. In the next slides, I listed a few open questions that those missions left. We really do not know very well what's the origin of the superrotation. We know that, for example, thermal waves, thermal tides or gravity waves maintain the superrotation, but what drives the superrotation is not clear. How waves, thermal tides, gravity waves, planetary scale waves interact with the general circulation is still something that we have to investigate, thanks also with general circulation 3D models. What is the detailed composition, the vertical side distribution, and the formation mechanism of the clouds? We don't know. That's why we have EnVision arriving in the next decades. What are the unknown UV absorber made of? There are some candidates, but still debated. What controls this variability, the variability of sulfur species? Something to be investigated. How the surface interact with the lower atmosphere, and how the atmosphere evolves over geological timescales. All these questions. This is actually on the right is what I was saying of this was during Venus Express, we found this large increase in SO2 after the mission, then a sudden decrease. So this was the kind of indirect evidence of volcanism during Venus. So let's go to EnVision. It will be the first. It will give us a kind of holistic exploration on Venus. What's the novelty? It will be the first mission able to study, to investigate from the from the core up to the atmosphere up to 100 kilometers. The other mission were focused on the surface, on the atmosphere, and EnVision will cover all this with all these instruments on board. We have the Venospec suite with 3 channels, U, H, and M. Which I'm particularly collaborating. The VENSAR is the radar in collaboration with the NASA participation. The subsurface sonder will be will analyze the interior and will go. Actually, it will be the first time that we'll be able to measure up to 1 kilometer deeper and on the surface of Venus. And we will have the radio science experiments. This is similar to we had on Mission. On Venus Express. So putting here some novelty, let's say, as I say, will be thanks to the interaction and the coordination with all these instruments, because we will have measurements of trace gases, water vapor, H2O, CO, CO2. From different instruments, we will investigate Venus system as a coupling, as a Venus system coupling, to have kind of synchronized search for active volcanism, not only from the spectrograph, but also with the radar, etc. We will, as I said, will probe the Venus upper crust for the first time with the subsurface sonder. We will have unprecedented higher resolution radar imaging, and the first polarimetric imaging of a selection region of interest. This is with the VENSAR. And for the first time with the radio science experiment, we will measure H2SO4 in the liquid phase. It was measured in the gaseous phase, but not in the liquid phase. So, as I said, this mission will start operation mid-2034. Meanwhile, we can work with models. We won't have observations. So this is the model, the 3 models that I'm working with, which is the former LMD. LMD stands for Laboratoire de Météorologie Dynamique in France. So this model was actually inherited from the Earth model, then was adapted to Mars and also to Venus. Now it's just changed of name, Planetary Climate Model, Venus PCM. I put here some references just for you. Since the beginning, when it was developed in 2010 by Sébastien Lemonois and other references. So the last reference paper is by Antoine Martinez in 2024, which also includes the ionosphere. So basically, the goal is to accurately simulate the details of the planet meteorology only using universal physical equations. So well, when we talk about the climate system, it's well, a very complex system. So the climate and a planet taking also into account the different number of degree of freedom, the interaction of waves. The waves interact with themselves, with the whole atmosphere, etc. However, the physical and chemical processes that work in a planet are a finite number. For example, we start with the radiative transfer of a source, in this case the sun or another star that interacts with the gas and aerosols, and the large-scale circulation, mostly radiatively driven circulation due to different gradient of temperature. And we have to take into account also the low-scale dynamics due to turbulence, convection, and the one layer. We can include or not some occasionally, for example, the impact of dust, or the impact of ice, the phase of the change of phase due to condensation, sublimation, evaporation, and we have to include not depends on what we want to study, the photochemistry. So depending basically on the planet characteristic, on the orbit, on the kind of stars, we can put all these ingredients together, but we can have different kind of climates. Even if the main processes are the same, are the finite number. So briefly, how GCM work? We have it's like we idealize, we divide the atmosphere in cells. So we calculate the state of temperature, composition, winds in each cells, in which we ideally divide the planets. And the GCMs are composed of two parts. One is the dynamical core, which is common to all, in this case, terrestrial planets, Earth, Mars, and Venus. And the other is the physical part, which can change depending on the planets. So the dynamical core includes the equation, general equation of atmospheric circulation to compute the large-scale atmospheric motions. And the physical part includes the physical parameterization. So depending, we want to study the lower atmosphere, the upper atmosphere, the physical parameterization we can include can be different. So basically, it helps to give us the output like radiative heating, cooling, surface thermal balance, and subscale atmospheric motions. The Venus PCM that I'm using, we have now a web interface in which you can download different variables. This is a project led by Sébastien Lebonnois. You can contact him. We can also have, this is the web interface, but you can also have the outputs on your computer. You can set the temperature, the density, the winds, or the abundances that we produce, different times and spatial coordinates. So let's go to the second part. We'll talk a little bit what we are currently working on in support of EnVision. As Helmut explained, I mostly work on the upper atmosphere, but now since EnVision will not observe as higher as we wish, I'm working in collaboration now with my colleague, especially this is the work done by our PhD student, Alberto Mendi, the IAA. The initial problem is that we have in the clouds, this is called the SO2 reservoir issue. What is this issue? This issue is that, we cannot see very well. Yeah, sorry. Well, the issue is that in the deep atmosphere, I'm talking about here below 40 kilometers, that we don't see here, but below 40 kilometers, the observations give 1 ppm of 100 ppm, about 100 ppm of SO2. Above the clouds, we have 100 ppb. So we have 3 orders of magnitudes a difference between the deep atmosphere and the high atmosphere. But here you can see that the shaded line are different observations in which also we can see the higher variability that we have of SO2. So focusing only on this blue line is the results from the model, where we have here initialize at 10 ppm. So it's we can reproduce what we call the depletion of CO2 in the clouds, only 2 order of magnitude of instead of the 3 that is observed. So this is an issue for all models. Actually, no models can solve this issue. But there are several hypotheses that these several institutes are working on. One of these hypotheses is that in the clouds, so this decrease in this depletion is produced because in the clouds we have salt. So hydroxide can be a proxy of salt. And this is a work that was, a hypothesis that was given in this work by Rimmer et al. That we are following, and that you know this study. Happy that you know this study. So the first step that what we are doing is to include into the Venus PCM these reactions that emulates the dissolution of the clouds following this work by Rimmer. Of course, there are preliminary results. This is a work by our PhD students, and what we have. What we have is that if we include those reactions into the model, there are a lot of lines here. Just focus on the green one, which is the SO2 and the gas and the liquid. So we do have the SO2 in the liquid phase, and the region of the clouds where we are expecting that the SO2 could be in the liquid phase. However, the SO2 gas is too much depleted now. So this is probably, there could be several reasons for that. First, because we didn't reach the steady state. Second, because those reactions and the reaction rates are adapted for the 1D model. We are working here on a 3D model, so there are also circulation to take into account. However, the good news is that here we can initialize below the clouds SO2 as observed, 150 ppm. But now the next step it will be, because these are there are only reactions emulating the SO2 dissolution, because Rimmer is proposing the full set of reactions that can explain this depletion. So the next step would be to implement the full set of reactions to reproduce the full in-droplets chemistry in the future. Another work where we are working on is on the dynamics of the upper atmosphere. So Venus basically has 2 main dynamical flows. The one dominating in the lower mesosphere, which is the so-called retrograde superrotation, which winds reaching 100 meters per second. Above, in the upper atmosphere, we have the subsolar to antisolar circulation, and in between there is a so-called, we call the transition region, because it's transition between these 2 regimes. And this is a very, very dynamical, very interesting region, also because we don't have measurements. A way that we can do to study this region is to use the OTI globe. This fluorescence you basically produce when this is the daytime, nighttime, and the day side the UV flux photodissociates CO2 to produce oxygen atoms that travel by the subsolar to antisolar circulation to the nighttime, and here's where they recombine the 3-body recombination to form the characteristic fluorescence at 1.27 microns, what we see here. So basically, this is traditionally used as a tracer in the upper atmosphere. We are talking here, it's 95 kilometers, so it's really in the transition region. Venus Express, so we have here VERITAS observation. So something that I missed to say that is, I think it's important, so if I can go back, no, I can go back, is that if the subsolar to antisolar circulation was symmetrical, we are expecting to see this emission here and the antisolar point, so kind of concentrating at the antisolar point. Instead, what VERITAS Express was statistically found that this emission is located at the antisolar point. However, as you can see here, there are instantaneous map, latitude and local time. We have also bright spots at higher latitudes. It indicates that we have large variability in this region. So the work that we have done with the model, it was published 4 years ago already, with Tomás Navarro. Here is a GIF video. So this variability is very difficult very difficult to represent with the model. We managed to represent this. This is the fluorescence with the kind of bright spots located at higher latitudes as observed. And this was interpreted in the paper as the propagation of 5 days Kelvin waves, which propagates westward, and enhance the poleward, the injection of O2 SEO at higher latitudes. And this is how we interpret this variation. However, we are not really able to reproduce the intensity of the map or the emissions. It's something that we are working on, and we have also to take into account, that's good for that to have a 3D model, that the motion cannot be explained only by horizontal motion, but we have to take into account vertical transport and chemical reactions to contribute to the emission. And that's something that we are working currently. I'm not going to enter into details, sorry, on this work that is in preparation. Just to give you an idea of what we are doing, as I said, in the physical part, we have several parameterization. One of those parameterization is the non-orographic gravity wave parameterization, which has several unconstrained parameters. One of those parameters is the so-called EP flux, which give an idea of the gravity wave amplitudes. So what we have done with the model is to evaluate how much those unconstrained parameters impact the circulation in this transition region. So in this figure here, we'll be brief on that because there are too many details, but just you see here the zonal wind and nighttime. So there's a region that we are interested in as a function of altitude. The black line is what we have, the benchmark reference model that was published by Anton Martinez 2024. And the red and the green is the effect of varying these unconstrained parameters of gravity waves. So what you see that the two main aspects is the stagnation point. This is where the zonal winds converge to zero. They change depending if we have westward or eastward impacts of the gravity waves. The superrotation, remnant superrotation, which is called here, because we have the superrotation at the altitude cloud top 70 kilometers. We also found it's something that's found by simulation, kind of remnant superrotation in the model, peaking between 100 and 125 kilometers, depending on the amplitude of gravity waves. And of course, it has some consequence on to O2 flow. That's something that we are working on. What we work with modeling is important, the two things, the comparison with observations and the validation with other models. What I've got here on the left is a compilation of nighttime temperature measurements at the equator from Venus Express and from ground base. So this is from roughly 75 to 130 kilometers. In black, you see there are the model results. In general, we see that we reproduce fairly well the behavior, except from data from SpeakUp, which shows this local warm layer warmer than predicted and even warmer than other observations. However, we can say that we are on the night side, we are reproducing fairly well the observations within parts up to 130 kilometers. If we go higher up, so this is another work we are working at IEA, it's the intercomparison project. Here we are comparing 3 models, thermospheric model. Well, I forgot to say that the one that I'm used as a Venus PCM is the only one which is able to simulate the atmosphere of Venus from the surface up to the exobase. The VT-GCM is the model led by US people, Amanda Brecht, Steve Booker. It's a thermospheric model, so just started from 80 kilometers, and this is the Japanese one, TU-GCM. Also, it's a thermospheric model. What happened here? What we have here, we have the data, and the dots are from Pioneer Venus observation, the equatorial region, and the blue and the lines are models. So at the night time, so this is the values of exospheric temperature versus local time. So here is a night time. We have good agreements. We are within the data dispersion, more or less. But during daytime, all the models are warmer. So we are overestimating the temperature. So we have a problem. So that's why this intercomparison project is very interesting, because we have to understand, because it's also important for the future mission to know what is the temperature, what is the density at those higher layer. How we interpret this? We interpret this because we, all the three models, underestimating the atomic oxygen. Atomic oxygen has play an important role in the cooling of the upper atmosphere. It's a non-LT process. And since it's focused here on the red points here, okay, what we represent is oxygen, CO, nitrogen, and CO2. So the red points are data from also Pioneer Venus neutral mass spectrometer. And the red lines are the models. So depending with the Venus PCM in particular, which is the solid line, we are up to...
Do you mean some oxygen line cooling or something like that? I mean, in the thermosphere, some cooling related to...
Yeah, it collides with CO2.
Yeah,
and it plays an important role in cooling the... Above 120
in the thermosphere. So.
Exactly. Okay. So we have a deficit in oxygen. We have higher temperature.
Yeah. It's interesting.
Yeah, that's what we have here. And we have another problem. Here we have the mass density measured this time by Magellan aerobraking. Here. And we have the three models, as you can see. Except from the VTGCM, all other models also fail in reproducing. This is that mass density at about from 135 to 142. This is the status of the three models right now. So we have a lot of work to understand what's going on there. Here is another example of these are aerobraking. I was focusing a little bit more on upper atmosphere because you are working on upper atmosphere. So there's another example of measurements of density. This time with the Vexad experiment, with torque, pod experiment, etc. So we have the dotted here. We 140. So the blue lines are what we call the VIRA, Venus International Reference Atmosphere, was also, you can see, overestimating the temperature. So the red model here is just an interpolation. So it was built upon the data. So all models overestimate the observations. Could be because the model I'm using, from 30 to 70%, we're overestimating the density. VIRA was estimating, depending on the altitude, up to 40%. Also, as you can see here in the lower, sorry, if I'm sorry, the time. You can see in the figure below also the higher variability. That is due in this case, the orange to the gravity wave propagation, as you can see here, that we are also working. EnVision will not observe density. I mean, it's not one of the main goals of EnVision. However, fortunately, we will have this long aerobraking phase. It was initially planned for more than 15, 16 months. Now it's reduced to 11 months. Thanks to this aerobraking phase, it's like for bonus science, we will have upper atmosphere measurements. It's clear that we need more measurements in the upper atmosphere. So the aerobraking phase will reduce basically the very initial elliptical orbits to a more circularized orbit from 200 to 500 kilometers. During this phase, so the satellite will be with the solar panel facing the direction of the flight, and will be able to measure the density with the drag of the satellite, atmospheric drag. So basically, I plot here summary of the previous measurements of area breaking. As you can see, with Pioneer Venus, Magellan, we were covering most all solar local time. We're more focusing on the equator, or the northern hemisphere. Venus Express, we had measurements here and the higher latitudes, but only at the terminator. So with EnVision, we will have, we were also able to study the variation of the density with the solar cycle. We're covering with the Venus Express, lower activity with the Magellan, with Pioneer Venus, higher solar cycle, higher activity. Thanks to EnVision, we will be able to cover these latitudes that was so to fill the gap of previous missions. But unfortunately, will be the only measurements of upper atmosphere we will have. Conclusion on this first part, it's that this is an exciting new decades coming from space exploration of Venus. We have 3 models are now fundamental to prepare new observations and also to study biases and to face new challenging measurements. The atmosphere about 120 kilometers is unfortunately poorly studied. Unfortunately, also because it's very dynamical and very challenging to reproduce and also difficult to observe. As we have seen, the 3D models struggle to reproduce neutral composition and temperature about 140 kilometers, and we need more observation on the upper atmosphere. Go to the last part, will be shorter than the, don't worry. Venus as an exoplanet. This is a work that I started actually years ago when I was in Portugal during, I had a Marie Curie project to work on that. I stopped for a while and then I plan to retake this project thanks to the funding that I got recently to hire postdocs, so I can continue the next year. So this figure show, as you see in the panel above, is our solar system planet, Venus, Earth, and Mars, with the Earth and Mars in the habitable zone, and Venus in the so-called Venus zone. And here it is a collection. This figure was not updated because it was done in last year, so will be probably more planets here populating this region. As you can see, most of the selection of Earth-like planets, discovered so far. You can see here the famous TRAPPIST-1 planetary system. And here, this is also the LP890c, who was a kind of interesting planet to study because it was a super Earth in the habitable zone. So as you can see, most of those new discovered Earth-like planets will receive stellar radiation similar to several times larger than the Earth. So it means that they could be, their climate could be more like than Earth-like. So that's why it's important and interesting to study Venus as a natural laboratory for those exoplanets that have been discovered so far. So in this the study, we focus on these 2 planets. I said this one because it was interesting, because it was a super Earth in the habitable zone, and TRAPPIST-1c because before James Webb's observation, it was TRAPPIST-C is exactly here. It's like it's very close. It's in the Venus zone. How we study exoplanets, basically we use the same model, the same dynamical core, and we apply this. I use the generic planetary climate model, also initially developed in France and and with collaboration on other institutions. And the dynamical part is the same, as I said, the physical part. We assume that the model, the atmosphere, we assume that the we assume that their atmosphere evolved into modern Venus, so it's an assumption. And also we use an endur star, that's the flux of the star, to calculate to make our simulations. So to be more detailed, what we have done, so for the case of TRAPPIST, for example, so the flux of the star was taken from the literature. Our orbital parameters for TRAPPIST were also taken from the literature. So we assume that it's a synchronous rotator. And this is the Venus-like stuff. Well, for the atmosphere, we assume that the planet has a surface atmospheric pressure of 92 bar, like Venus, similar components composition as Venus, and we completely cover the planet with a prescribed global cloud deck made of sulfuric acid. For that, we follow previous work of the inclusion of radiatively active Venus-type clouds into the model. One other interesting application of this global circulation model applied to exoplanet is that we can produce planet-to-star contrast phase curve, thermal phase curve. So here is an example in the continuum, and then the 15 micron band, which is a stronger CO2 absorption band. Well, in this case, we don't see with the thermal phase curve, we're probably familiar with, you can infer dynamical properties. You can see if there are jets or hotspots, if the hotspots are shifted. So you can infer dynamics by studying the planet-to-star contrast. So basically, here the conclusions were that, well, we didn't find too much difference between the continuum 15 micron bands, and the largest amplitude that would permit indeed to detect hotspot, if any, it's too small and not detectable with current AFC. Yes, so this was one of the conclusions that of this study. For TRAPPIST-1C, what we did was, well, the same. And it was the work was done previously by my former PhD student, Diogo Quirino, and continued by another master student last year. As you can see here on the right, there are results from James Webb's observations. This is probably you know already this figure. The red dot, the red diamond is the observation at 15 micron, where we have this strong CO2 absorption band, and they were comparing the data with error bars with several models. Okay, one, for example, the yellow one is the cloudy Venus with 10 bar surface pressure. And you can see that the planet-to-star contrast in ppm was smaller than expected. So this study suggested that this exoplanet doesn't have CO2-rich sulfuric acid clouds, and probably that suggested that it has a thinner atmosphere or a bare rock surface, because this is more consistent with observation. With this model, we have what we have done in the last development was to include a module that allow us to form clouds interactively, where the temperature and pressure are favorable for the condensation of sulfuric acid. We were also kind of playing with the shape of the clouds, the cloud structure. I don't want to enter into details, but just to show you the different lines here represent also different acidity, etc. And all the cases, the planet-to-star contrasts are smaller than what was observed. So it's kind of supporting the conclusions that TRAPPIST is at. So this is a kind of application that we can do with our GCM. I think I'm going to the end. Of course, this is a conclusion for Venus analogs. Well, at this phase, we can speculate on the atmosphere of the planets because the results that I showed are based on the hypothesis that the atmosphere of the planets evolved in the modern Venus, but we don't even know if they have an atmosphere. We don't know anything about the composition of the atmosphere, in particular, the composition of a planet around the M dwarf star. We don't know if the sulfuric acid clouds are common on our exoplanets, and we have a lot of uncertainty, planetary parameter, rotation rates, etc. Also, the temperate Earth-sized exoplanets, they have a small scale height. So if they are, especially if they are cloudy, and as you know, the transmission spectra will be flat. So the temperate Earth-sized planets are not favorable for transmission spectroscopy with current instrumentation. You had to wait the future is alive or is the new instrumentation on board ELT. So for now, what we can do is still working on modeling in particular and this strong, for example, absorption band that are more promising because larger planet-to-star contrast and amplitude. So let's see the future. And I conclude here. Thanks for your attention.
Yeah, thank you for the very interesting and nice talk. So questions. So maybe first, yeah. Are there someone of the younger people?
I don't eat.
Then maybe let's start with the.
So I have two questions, one for the Venus and one for the exovenus part. For the Venus part, do I understand it correctly that you use the Eliason-Palm flux to kind of parameterize the superrotation in your?
Repeat that. I use what?
The Eliason-Palm flux, the EP flux. Is this a parameterization of a superrotation, or what do you do?
No. The EP flux. Yes, the EP flux is a parameter that we use to simulate the propagation of non-orographic gravity waves in the atmosphere. We assume that because we have several gravity waves, the stationary waves that the one produced by the surface of topography, example, the mountain. So they propagate, but non-orographic gravity waves are not non-stationary gravity waves.
Yeah, that's true. They're transient and vertical, and then you're used with the EP flux. And how do you get superrotation? Because you do not. How do you actually get superrotation? I mean, at the correct height and with good speed.
Rotation.
Yes.
The superrotation is obtained after, I think, Sebastian was running for 200 Venus day. We have, I don't have figure here, but we simulate, we
capture them.
Yes,
Okay, good.
The superrotation.
Okay, good.
Access with there's a work I can show you later.
Okay.
We produce
well, so can show me after the talk for more detailed discussion. Maybe the second question for the exovenus. You played Venus and then tried to do a thermal emission. Have you considered that these planets that are so close to an M dwarf are actually super oxygen rich? So it's not actually a real Venus analog, but a kind of 100 bar O2, which also is in there, so a more exotic atmosphere composition, and checked what this would do. But
it's a good question. There's something actually I would like to do is to because we started with a strong assumption that these exoplanets around an M dwarf has the same composition as Venus. But actually, maybe here have an extra slide. There was this one. There was a work by Jordan. It's with the same group of Rim, if I'm wrong. But what we have to calculate is what happens and what they do with the 1D model is to put the planet around an M dwarf star and calculate it how much the sulfuric acid increase or decrease depending on the kind of star, the host star. It's not done yet, but it's something that I would like to do with you. Because of course, for the sulfuric acid could be what they found here. Actually, here they do it with several kind of stars. You see from M to G, and they found a decrease of H2SO4 liquid with the stellar activity. Okay. But of course, it's something that we
So basically, you can only really exclude an Venus twin. It doesn't mean that you cannot have other more exotic.
Something that actually should be done more properly. It was just at the first test to see, okay, we assume that now the planet has the atmosphere of Venus, but it's probably not correct. It's surely not correct.
Yes. I wanted to ask a fundamental question about the cloud formation. So the clouds are very important for the radiative transfer, for everything, even for the chemistry. So, and my understanding is that you form actually really, so the clouds are part of your model, yeah? When you run the time-dependent model, you produce these clouds, or how is your prescription? How do you treat the clouds?
Yeah. Try to explain is not my expertise, but I try to explain. So this actually in the paper by Stolzenbach, it was the first time that the photochemistry model and a simplified model on the model. So this is not, we do not take into account the nucleation and growth of the particles. We start from, we consider the distribution of the droplets following the observations.
Mm-hmm.
This is our starting point. But then in the model, we calculate condensations, sedimentation, evaporation. So it's not.
But you first have to set the cloud somehow.
Yeah, we set the cloud with the observation with the instrument on board of Pioneer Venus. So the vertical, the size and the distribution of the droplets are prescribed.
Mm-hmm. But the amount of it's not, yeah. So when you have the conditions to form,
well, we calculate the number density is calculated.
all right. So the only prescribed thing is the size distribution of the particles.
Yeah.
But can the particles also sediment?
Yeah.
They do. Right?
Yeah, they do. Yes.
And once you go too deep, then stuff comes off again, right? So then you repopulate.
Yeah, I can give you the details if you want, but it was not the part. I didn't develop this part. But
Would be interesting. The paper I would like to know. We can talk about it. Yeah.
I have also a question regarding or two maybe. First, for these exoplanet studies, I would expect that you applied this let's say the model not together up to an exobase level, right? I mean, only the lower atmosphere. Because I mean, what you have here, what Martinez, I think, is your colleague, where you said that this model he applies now also goes from the ground up to the exobase. So he has included the thermosphere for Venus. For Venus.
This is Venus. So you're talking about Venus.
For Venus, right?
Yeah.
But for the exovenus, it was maybe up to 100 kilometers,
Yes.
right? So I would recommend to apply this other model, because then you would have the whole thermosphere included, and the M stars have these 100 times or more higher fluxes. So then maybe, I don't know, I would expect that there is no atmosphere or not much. I know we may be all exciting on that.
For one
But
thing, I
this
agree.
type of model, because if you neglect the upper atmosphere, which you have a UV flux 100 times or more higher, it will change everything. It's my opinion. So if there would be if this model exists, it would be interesting to apply, no?
Definitely, yes. I explain you why it's not done yet. Because going up to 100 kilometers is not just extending the model. You have to include all the processes.
Yeah, I know.
One of those processes is non-LT.
Yeah. It may be not even, it may start to get hydrodynamic even in the top, or expanding.
Yeah, it's not just, okay, we go up, but there are processes going on there that we have to take into account.
Something to keep in mind for the future. It would be at least my wish that someone has such type of model. And the other thing related to Venus, I mean, do you plan or do you or Martinez include the deuterium chemistry? Discuss this.
The deuterium chemistry was included by the PhD student.
Okay, so
supervised by Franco Messan and Frank Lefebvre. It is included. I'm not sure that this version is already committed, because every time there's an improvement, we commit, and we have. So the version that we use right now doesn't include it.
But hydrogen, of course, all this is there. So
Yeah.
For instance, you can model in the thermosphere with the 3D code the hydrogen-related molecular ions.
Yeah, this is included, and I think that I'm not sure, but Gianni Chauffret was doing some implementation to calculate the hydrogen escape. Yes, I have to. But yes, yeah.
People start to disappear, yeah.
Is there some last question? So, yeah.
Just a technical question. What is the orbital plane of EnVision?
Orbital.
The orbital plane
Of EnVision,
of EnVision.
the orbit.
It's a circular, no?
It's circle 200 kilometers up, but where is the orbital plane? And the equator and the
Yes,
polar
it's
mixed in.
No, the polar, sorry, I'm confused, and with another mission I was involved too. It's kind of
it looks like polar.
polar, like was a mission. Venus Express.
This
so
is
it
also
was more-
polar, of course.
Similar to Venus.
But would not cover.
It's again polar. Okay.
But it's an eccentric orbit, right? It's an eccentric orbit.
Is that circular? Going back.
Circular, kind of.
Circular?
You see here from two,
200 to 500.
kind of circular.
Circular.
But you need to change somehow the axial motion, because otherwise you cannot do gravity measurements, right? I mean, you need to change the orbit. I mean, the longitude, right? You're changing. Otherwise you can't do gravity measurements. You need to have the gravity field measurement.
Consider that the final orbit is not,
Okay.
fine, okay.
Okay, so if no questions, then let's thank our speaker again.